Yes, sir. Let.
Yes. Hello all. So welcome to the iitian Gate classes. Can you hear me, sir?
Yes, sir.
Yeah. So hello all. Welcome to the iitian Gate classes. In this particular session, we are going to cover the solution of fluid mechanics and hydraulic machine of Gate Mechanical 2022 paper, right? And this is a solution regarding the set 2. In the last class, we have covered the set 1 solution of the same Gate 2022 paper, guys, right? So here in this particular session, first of all, we would like to cover the what are all the weightage for this particular subject in the section B, right? So you can see here the weightage part regarding the fluid mechanics and hydraulic machines. And again, I'm mentioning here that hydraulic machine, not a single question is being asked, right, from the hydraulic machine in the set 2 as well as in the set 1 in GATE 2022, right? But again, you should not neglect this particular subject. Again, the 2 mark question will be asked in 2024, right? Now coming to this 1 mark question, the total number of 1 mark question were asked of what, guys? The two questions, right? And the three questions were asked of 2 marks. So the total number of question uh, regarding this fluid mechanics and hydraulic machines were 5 questions, and the total weightage for this particular subject is 8 marks. This particular subject is carrying the weightage of 8 marks in the section B, right? In the section B, we have some other subject like thermodynamics and its application, along with the heat transfer, again, along with this fluid mechanics and hydraulic machines, right? So it is one of the important subject, as you can see in the set one also 8 marks, and here also 8 marks, right? Same you can expect in 2024 also around 6 to 8 marks. Coming to here, question number one. In the question number one, you can see, guys, consider a steady flow through horizontal divergent channel as shown in the figure with the supersonic flow at the inlet. The direction of flow is from the left to right. So you can say at the inlet of the divergent channel there is a supersonic flow. That means Mach number is more than one, right? And what they have mentioned that the pressure at a location B is observed to be higher than that in a, what, guys, upstream location. That means the pressure at a point B is more than pressure at a point A. Which of the following option can be the reason? Now, by looking at the options, what they have mentioned, since the volume flow rate is constant, the velocity at B is lower than the velocity at A, right? What is the second option? Normal shock. What is the third option? Viscous effect. And what is the fourth option, guys? Boundary layer separations. Boundary layer separations. Coming to the solution of this question, see, I'm drawing once again here the diagram. There is a divergent portion, and here I'm considering the flow to be left to right, and they have mentioned pressure at a point B is more than pressure at point A, and Mach number is more than one at the inlet, right? If you see the divergent portion, of course, there is a supersonic flow. That means it is a compressible flow. So definitely we have to look it into what compressible flow point of view. Before looking into this compressible flow point of view, if you know the what is the relationship between area and the velocity, guys? dA over A, which is equal to m square minus 1 into dB by V. This particular relation is very, very important, guys. By this particular relation, what you can understand, from A to B, the area is increasing. That means dA is positive. If you are moving from A to B, area is increasing. Definitely change in area is increasing. What you can see that the change in area is positive. What about Mach number? This quantity is positive. Mach number is square minus 1. That is also positive. So what you are expecting? You are expecting that the velocity should increase, right? What is the expectation? The velocity at a point B should be more than velocity at a point A. That means it should behave like a nozzle, right? According to the equation, it should behave like a nozzle. And if you see the pressure and the velocity relationship. If the velocity at a point B is more than velocity at a point A, then definitely pressure at a point B should be less than pressure at a point A, because they are inversely related, velocity and pressure. And if you see corresponding to this one, this should be the condition that should be given in the problem, but they have given in the problem PB is more than PA. Definitely this expectation is not correct, whatever we have expecting here. So definitely something is happened between A and B, right? And that happening is what, guys? There is a normal shock. Normal shock, you know that there is a sudden change in property across this particular shock waves. And this normal shock is what, guys? It's an irreversible and adiabatic phenomena. Irreversible adiabatic phenomena. What happened when there is a normal shock? What happens when there is a normal shock? Now, before looking into the understanding of this normal shock here, if you see what actually happened because of the normal shock. Because of the normal shock wave, supersonic flow gets converted into subsonic flow. Subsonic flow means the velocity will decrease. The velocity will decrease, and when the velocity will decrease, the pressure will increase. So, what is the exact reason for happening? No, before reaching this conclusion that pressure at a point B is more than pressure at a point A, what is actually happened? The normal shock wave is being formed in between A and B. That's why if there is a pressure at a point B is more than pressure at a point A. So what should be the correct option, guys? Normal shock. When you look at the option D, there might be confusion. The boundary layer suppression, because you know that in the divergent portion, because the pressure is more, because at the outlet of this divergent portion, the pressure is generally higher than the inlet section. In a thinking of that way, what we may think, we can think that there is a flow suppression. The flow will be getting reversed from the one side of the wall, and we may start thinking that that could be the reason. That could be the reason, but that particular thing will be applied, that boundary layer separation will be applied when you have the subsonic flow throughout these particular sections. When there is a subsonic flow throughout this particular section, that means no, there is a no compressibility effect. There is a no compressibility effect, because you know that whenever the any particle is moving at a very high speed, then only the compressible nature will be coming into the picture. Then only Mach number will be higher. Then only the shock wave will be forming. There will not be any shock. There will not be any kind of normal shock when there is a flow is what? Subsonic flow at the inlet. The moment you are moving your vehicle or your plane at a very high speed, more than Mach number 1, then only the shock wave will be forming. So by giving the region like because of the boundary layer separation, pressure at a point B is more than pressure at a point A, that is not correct, because inlet flow is what? A supersonic flow. That is not a subsonic flow. Because if this divergent portion would have been the condition like given it as Mach number less than 1, that means if it is a subsonic flow throughout these inlet and outlet sections, then we might be thinking that this divergent portion will behave like a what? Diffuser, and the velocity will decrease and pressure will increase. And then we may start thinking this is this may be the reason, no, because of this reason pressure at a point B is more than pressure at a point A. Because of that only the boundary layer separation is taking place. It's not because of the boundary layer separation the pressure at a point B is more than pressure at point A, right? So in any way this D option is not at all correct. Unnecessarily they have kept this option to confuse you, and it is very high chance that you will get confused among B and D. If you don't know any concept regarding compressible flow, you will tick option D. That is absolutely wrong, right? So that is regarding question number 1. Now coming to the question number 2, guys. Here again, if you're thinking that viscous effect, there is no role of a viscous effect in this particular case. There is a compressibility effect is there, not a viscous effect, right? Now coming to this question number 2 here, try to read the particular problem, guys. The velocity field in the fluid is given to be the velocity vector u I cap plus v j cap. Which of the following statement is correct? The velocity field is one-dimensional. The flow is what? Incompressible flow. The flow is irrotational. The acceleration experienced by the particle is zero at x equal to 0 and y equal to 0. Which of the following is or are correct? Now, before answering this question, the first you can eliminate the option, guys. This is incorrect. Because you can see the velocity vector they have given u I cap plus v j cap. Definitely the flow is what, guys? Whatever the velocity u is what, guys? It is a function of x and y. V is also a function of what, guys? X and y. So definitely it is a 2D flow. Definitely it is what, guys? It's a two-dimensional flow. Because you need the x coordinate and y coordinate, both the coordinates are required to specify the particularly what, guys? A velocity flow field. So it is not a it is not a one dimensional, it is a two-dimensional. Coming to the B option, the flow is incompressible. What is the equation? First of all, note on the velocity vector, guys. 4xy I cap plus 2x square minus y square j cap. Now, for an incompressible flow, what is the u? 4xy. What is the v? 2x square minus y square. First of all, for checking the option 2, whether it is correct or not, for incompressible flow, what is the necessary and sufficient condition, guys? For an incompressible flow, volumetric strain rate to be 0. That means what we can say that del dot v should be 0. That means the velocity vector should be divergence free. We can also write it as dou u by dou x plus dou v by dou y plus dou omega y. But here the velocity vector in the third direction is 0. So this dou omega by dou w by dou z will also be 0. What is the dou u by dou x? It's a 4y. What is the dou v by dou y? It's a minus it's a minus 2y, so which is nothing but minus 4y. So it is 4y minus 4y, and if you see that, it is equal to 0. So left hand side is equal to right hand side. So what we can say, guys, here we can say very clearly that it is an incompressible flow. If you see the third option, the flow is irrotational. For the flow to be irrotational, the angular velocity about z-axis should be 0. And if you write the formula, half of dou v by dou x minus dou u by dou y should be equal to 0. What is the dou v by dou x? It is a 2 into 2x, which is nothing but 4x. What is the dou v by dou y? 4x. So 4x minus 4x, it is equal to 0. So again, the flow is what, guys? It's an irrotational flow. The third option is also correct. What about the fourth option, guys? What about the fourth option? Fourth option, if you look at, they are asking what is the acceleration, experienced by the fluid particle. Very first of all, what is the acceleration for two-dimensional flow field? Ax, which is nothing but u into dou u by dou x plus v into dou u by dou y plus dou u by dou t. But again, it is a steady flow. This will be automatically 0. So here we can write ax. What is the u? 4xy. What is the v? 4xy. What is the dou u by dou x? 2x square minus y square 4x. If you try to substitute at x equal to 0 and y equal to 0, you are going to get 0. Similarly, ay, if you try to find it out, what you can get, guys, u into dou v by dou x plus v into dou v by dou y. Plus v, what is the v? 2x square minus y square. Dou v by dou y is what, guys? Minus 4y. Again, if you put x equal to 0 and y is equal to 0, you are going to get 0. If you read the problem, what they have mentioned, the flow is incompressible, the flow is irrotational, the acceleration experienced by the fluid particle is also 0. So B, C, D is correct option, not A. A is not correct. Now, coming to the third question, try to see this question, guys. If you have any doubt, let me know. The tube of uniform diameter is immersed in a steady flow, flowing inviscid liquid stream of velocity v, as shown in the figure. The gravitational acceleration represented by g, the volume flow rate through this tube is what? So first of all, we will make the diagram here separately. Here, what they have given? One thing before answering this question, I would like to ask whether it is a pitot tube or not. So this is not a pitot tube. Because if this would have been the pitot tube, the answer must be 0. The answer must be 0 because the fluid becomes stagnant in the tube. It will not flow. This is the point 2. This is the point 1. And I'm considering one more point. This is a point 0, for example. What I'm going to do, I'm going to apply the Bernoulli equation between 1 and 2 first. And then I will be applying the Bernoulli equation between 0 and 1. So whenever the fluid is flowing at a velocity v, so what is the velocity at a point 0? It's a v. What is the pressure at a point O? What is the pressure at a point O? This is the, for example, atmospheric pressure, for example. Then we can add P atm plus rho g h1. Suppose P atm you are taking 0, then P naught is what, guys? Rho g h1. And why we are able to apply the static equation, even though fluid is moving? We are applying these static equations. We are considering what, guys? We are considering perpendicular to the flow. We are considering the flow to be perpendicular to the flow, right? And perpendicular to the flow, there is a no flow. So fluid will behave like a what? Static fluid. When you apply the Bernoulli equation between the point 0 and, for example, this is the point 2 dash, and when you try to apply the Bernoulli equation across this streamline, you will end up getting what? This equation. Pressure is equal to what? Rho g z, where z is what, get h1, right? So even the fluid is flowing, we can still apply the static equation in a moving fluid, because what? If you try to apply the Bernoulli equation across this streamline, not along this streamline, you are end up getting what? Hydrostatic equation only. Hydrostatic equation only. Why you are end up getting hydrostatic equation? I told you the reason. Perpendicular to this streamline, there is a no flow. Along this streamline, the net velocity is there, net flow is there. If there is a no flow perpendicular to this streamline, the fluid will behave like a static fluid, right? So try to apply the Bernoulli equation. Zero and 1. So P naught divided by rho z plus V naught square divided by 2g plus reference here. If you take the reference, this as a reference, for example, then height is same for a point 0 and for a point 1. So what you can write here, z0, which is equal to P1 by rho z plus V1 square by 2g plus Z1. Z1 and Z naught is same here. So what we can write guys here further? We can write here P naught by rho z. Again, what we can write guys here? P naught by rho z is what guys? P naught by rho z is equal to H1. So H1 plus V square over 2G, which is equal to P1 by rho g plus V1 square by 2G. Equation number 1. Again, apply the Bernoulli equation between 1 and 2. Apply the Bernoulli equation between 1 and 2. So P1 by rho g plus V1 square by 2G plus Z1, which is equal to P2 by rho g plus V2 square divided by 2G plus Z2. Again, understand P2, what is the value of P2? P-ATM. And again, we are considering it to be 0, for example. You can take it also, no need to worry, it will be cancelling out. And what is the V1 and V2? It's a constant diameter pipe. It's a constant diameter pipe D. So V1 is equal to V2. So this will also be cancelling out. What about the reference height, guys? It's a Z2 here, and here we have the height of, for example, Z1. So Z2 minus Z1 will be what, guys? It's a H1 plus H2. So what we can write here, what we can write, guys? We need to get the values from the equation number 1. And what we can get here, guys? P1, which can also be written as rho g, Z2 minus Z1, which is nothing but H1 plus H2. So if you write in the equation number 1, put in this equation H1 plus V H1 plus V square over 2G which is equal to H1 plus H2 plus V1 square over 2G. So this will be cancelling out. So here what you can get, guys, you can get here V1 as under root of V square minus 2G H2. And what is the discharge, guys? A1 V1. Through this one you can find it out what is the discharge, which is nothing but pi by 4 D square under root of V square minus 2GH2. So if you see the option, which option is correct? D option is correct. The key point for solving this particular problem is that first of all, it is not a pitot tube. Second thing is that this is step. The moment you get this step, all the things are clear. It's just that we need to apply the Bernoulli equation 2 times. Right. Now moving to the next question, that is the fourth question. The study velocity field, study velocity field in an inviscid fluid of density 1.5 is given to be the velocity vector in a 2D flow field. Neglecting the body forces, what is the pressure gradient at x equal to 1 and y equal to 1? So for this one, my dear friend, first of all, I'm writing the velocity field here. What is the velocity field? It is given y square minus x square to xy j cap. So very first of all, I'm going to apply the Navier-Stokes equation. What is the Navier-Stokes equation, guys? U into dou u by dou x, V into minus 1 upon rho dou p by dou x plus mu del square u. But they have mentioned that it is an inviscid fluid. What they have mentioned, guys, it's an inviscid fluid. Check it out. Inviscid fluid. Inviscid fluid, that means there is no viscosity. This will be 0. So again, this term will be completely 0. So what is the u component? It is y square minus x square. And what is the v component? 2xy. So y square minus x square dou u by dou x, which is nothing but minus 2x, 2xy dou u by dou y. Again, omega is 0. It is a steady flow. This also be 0. Minus 1.5 dou P by dou X. But they are asking at location X equal to 1 and Y equal to 1. So what you can get, guys, from here, uh, put that value. So what is the dou P by dou X? Minus 6 at X equal to 1 and Y equal to 1. Right. Again, apply the Bernoulli Navier-Stokes equation in the Y direction. So Y momentum equation, if you write, U into dou V by dou X minus 1 upon rho dou P by dou Y. So what you can get, guys? This is 0, this is 0, steady flow, and that's a 2D flow. It is 0 because of the 2D flow. It's a 0 because of steady flow. What is the U? Y square minus X square. Dou V by dou X is what, guys? Plus V. What is the dou V by dou Y? Dou P by, again, this is also 0. So here again, if you write down, you are going to get minus 6. So what is the total pressure gradient, guys? The total pressure gradient you can write here. The delta P, if you write, it's a minus 6I minus 6J. So what you can get, guys? Which option is correct? C should be correct. The pressure gradient at X equal to 1 and Y equal to 1. Remember that here, if you write down for the Y momentum equation, there will be certain body forces plus rho G. But these body forces, we need to neglect it. They have mentioned in the problem, we have to neglect it. Right? Moving to the last question, guys, if you see, the last question, guys, for this particular session, again, this question is being asked from the fluid mechanics here. What they have mentioned that a uniform wooden rod of a specific gravity, 0.6, and the diameter of the rod is 4 centimeter, and the length of the rod is given as 8 meter, is immersed in the water, and it is hinged without friction at a point A. The solid spherical ball made of a bleed having the specific gravity 11.4 is being attached to the free end of the rod to keep the assembly in the static equilibrium inside the water. For simplicity, assume that the radius of the ball is much smaller than the length of the rod. What is the radius of the ball? What is the radius of the ball? Very first of all, that is the weight of the rod. Weight of the rod is acting in the downward directions. Weight of the ball is also acting in the downward directions. If it is there in the fluid, so there will be certain buoyancy forces. Here also there will be certain amount of buoyancy forces. It is hinged about a point A. For example, here in the problem they have mentioned a point A. So here what I'm mentioning, point A. And there is a liquid here. What is the weight of the rod? Rho G volume. Weight of the rod, density of the rod. What is the density of the rod? Let's keep it like this. What is the volume of the rod? Pi by 4 d square into L. So we can also write pi R1 square into L. L1, for example. What of the weight of the ball? Weight of the ball is rho of ball G into volume of the ball, which we can also write rho of ball G. What is the ball? It's a spherical shape. What is the volume of the spherical, guys? 4 by 3 pi r cube, right? Now, what is the next particular task? You might be thinking, sir, we can do summation of forces in the y direction to be zero, but if we do that, there will be certain amount of reaction forces. There will be certain amount of reaction forces at the hinge point. So better to do summation of moment about a point to be zero. Again, this is one of the static equation, and they are mentioning that we need to keep the body under static equations, static equilibrium conditions. So what we can get, guys? Suppose from here to here, the length is what? It is x, and here to here, what is the length, guys? What is the length they have mentioned? Here, guys, if you try to think and apply a little bit of logic, a uniform rod is there, which is having a certain amount of mass, which is having certain amount of weight. It is hinged, and then the ball is being attached, and the radius of the ball is very, very small as compared to the what, guys? The radius of the ball is much smaller than the length of the rod. That means whole mass is concentrated at the center of gravity of this particular rod, we can say. So if it is x, then it should be what? 2x. There is no doubt. If it is x, it should be what, guys? It's a 2x, right? Because see, if this is the length and this is a ball, you cannot say that this will be affecting the center of gravity shifting, right? It is almost same because this radius of the ball is very, very less than the length of the rod. So it seems like center of gravity will be shifted to what? Exactly on the same the center of gravity of the rod for the whole body, right? Now, guys, what should we do? We should not take the moment. If we take the moment, then what we can write, guys? W of the rod into x plus W of the ball into 2x. That must be equal to the buoyancy force is 1 into x plus buoyancy force 2 into 2x. Now, what is the buoyancy force 1? Rho of fluid g into volume of displaced fluid because of the rod. So that means volume of the rod, because complete volume of the rod is immersed. It is not partially immersed, it is completely immersed. So what are the next task, guys? Here we need to find it out. What should be the volume of the rod? So it's a rho of fluid g into again pi by pi r1 square into L1. And what are the buoyancy forces, guys, here? Rho of fluid g into what is the volume of the ball? 4 by 3 pi r2 cube. So here weight of the rod which is acting in the downward into x, weight of the ball into 2x, that is equal to buoyancy force into x plus buoyancy force 2 into 2x. And then what is a thing we need to keep, guys, here? Try to substitute rho. G will be cancelling out from all the sides, so I'm not writing once again. Pi r1 square into L1 into x. X will also be cancelling out, so I'm not writing here again. Plus 2 times of weight of the ball. Again, I'm not writing G because they will be cancelling out. 4 by 3 pi r2 cube. That's it, guys. Now you have to substitute and get the answers. So I'm doing the solution once again here. Rho of rod, if you divide by rho of rod to the rho of fluid, you are going to get the specific gravity. You are going to get the specific gravity. What is the specific gravity of the rod? It's a 0.6. That means rho of rod to the rho of fluid. It is 0.6. And what is the specific gravity of the ball to the rho of fluid, guys? It's 11.4. So keep that value, guys, here. 0.6 pi. What is the r1 square, guys, here? What is the r1 square? What is the radius, guys? It's a 0.02 square into what is the length? Length is given as 8 meter plus 2 into 11.4, 4 by 3 pi r. What is the pi r? What is the value of r, guys? R2. That we need to find it out. That should be equal to pi 0.02 whole square into 8 plus 4 by 3 pi R2 cube into 2. If you try to calculate the answer, you are going to get R2 as 0.0358 meter. That means it is 3.58 centimeter. R2 value. You can do the calculations. You can simplify it. Let me do that. 0.6 into pi into 0.02 square into 8. If I subtract this with the pi 0.02 into 8, and if you take here divided by 2.8 minus 2 into 3 by pi by 4. So you're going to get 0.03587 meter. And if you multiply with the 100, you're going to get 3.58 centimeter. That should be the radius. That should be the radius. And what is the radius of this particular rod, guys? The radius of the rod, you got it like a 2 centimeter. Already they have given the radius of the ball is what, guys? 3.58 centimeter. That should be the answer. What should be the radius of ball? 3.58 centimeter. Again, you have to remember that you have to use the pi 3.14, right? So that should be the answer. That should be the answer for this question, guys. Remember that we cannot do. Some of you might be thinking, sir, weight of the rod plus weight of the ball, that is equal to buoyancy force 1 plus buoyancy force 2. This is incorrect because there will be certain amount of hinge reaction forces will also be coming, and that will, if you try to find it out, you cannot find the radius of the ball because R1 you don't know. That's why what is the better equation? Better equation is take summation of moment about point A to be 0 instead of taking summation of forces in the y direction to be 0. So that's all about this particular session, guys. Thank you all.